Hello again, Wade Hampton chemistry students. Today we've got the third installment of our lessons relating to electron configuration. And in today's lesson, we're going to be talking about valence and core electrons, some classifications of electrons inside an electron configuration. We're also going to be covering how to write a shorthand style of electron configuration known as a valence shell electron configuration or noble gas core electron configuration. And we're going to be talking about some patterns that pop up in the periodic table that relate to electron configuration as well. Okay? All right, so first of all, if you take a look at an electron configuration like the one shown here for the element sulfur, the core electrons in an electron configuration are going to be the ones that are in energy levels that are not the highest energy level. And in fact, they're also going to be equal to the previous noble gas. Remember, noble gases are group 18 in the periodic table. And so if you were to start at element number sulfur and back up in atomic numbers, 16, 15, 14, the first noble gas that you would get to would be element number 10, which is neon. So in other words, the first 10 electrons in the electron configuration here would be the same as the electron configuration for neon. This is the first time that you're going to have a stable electron configuration. And so these electrons make a stable core. And so all of the electrons that are inside that core, the 1s, 2s, and 2p here, would be the core electrons of sulfur, a total of 10 electrons there in those three different sublevels. So sulfur has 10 core electrons. Valence electrons, on the other hand, these guys are going to be electrons that reside in the highest energy level. You might remember from doing Bohr models and Lewis dots, if you were doing rings around the middle of the atom, only the electrons that were in the highest energy level were classified as valence electrons. Remember, highest energy level in an electron configuration like this is going to be represented by whichever number in front of your orbital designations is the biggest. And so it looks like the third energy level, either shown there or shown here, is going to represent where the valence electrons are. So those 2 and those 4 electrons, or these electrons, would be valence electrons in this model. Valence electrons are electrons in the highest energy level. So sulfur has 6 valence electrons, and sulfur's got 10 core electrons, according to this. Okay? Now, it's important to note that valence electrons and core electrons can exist in more than one orbital, because you often have more than one orbital within, or more than one sublevel even, within an energy level. So the 3s and the 3p here both make up the highest energy level, and there just happens to be 6 electrons in that highest energy level for sulfur. Now, if you start looking at the periodic table, that really the whole reason why the periodic table has this characteristic shape that it has is because of electron configuration. And the location of an element on the periodic table can really tell you what the last orbital being filled would be in that electron configuration for that element. What would be at the end of the electron configuration, just based on where it is. So for instance, just a second ago, we were taking a look at the element sulfur, and sulfur ended in a 3p4. The 3p was the last orbital, and it had 4 electrons in it. Well, if you were to look at this diagram, this area of the diagram that's shaded in red here is known as the p block. And if you were to look, the first time the P appears is in the second energy level, which is in the second period or second row of the periodic table. And so the 2P would be in that second energy level. The electron configurations that end in 3P would be in this third row of the periodic table in the P block. Okay, so the first element in the 3p would have an electron configuration that ends in 3p1. This element would end in 3p2. This element would end in 3p3. And guess where sulfur is on the periodic table? Sulfur is right here, showing it has an electron configuration that would end in 3p4, which we just saw in that electron configuration that was shown on the previous slide there. Okay. So if you just want to know the end of an electron configuration, say, you're talking about the element O lead, which happens to be right here, Pb, that's a big electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, blah, 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 all the way up to 6p2. Okay, I know whatever it is before it, it's going to end at 6p2 because that's lead's location on the periodic table. Okay. Now, if you start to compare the periodic table to the order of filling that we looked at before, this arrow diagram that shows the off-ball principle, really once you know where the S block, the P block, the D block, and the F block in the periodic table are, you could just follow atomic numbers to know what the order of filling is. This is element number 1, 2, 3, 4, 5, 6, 7, 8, and so on. And if you were to just follow row by row in the periodic table, you would fill in the 1s and then the 2s and then the 2p. Just like this says, you'd fill in the 1s and the 2s and the 2p. And that scheme continues, and it works. The thing that you really need to keep in mind if you're going to use the periodic table to do this is that the transition metals are one energy level below whatever the row number is. So if this is row number 4, notice this is the 3D in the 4th row. We've got a 4s and a 4p in this row, but the transition metals have the D block being at an energy level that is one lower than the other orbitals that are being filled in this row in the periodic table. And you can see that if you look at your arrow diagram here. We filled in the 4s first, right there, and then we went to the 3D after the 4s and went up here, and then we went to the 4p there. So you can see that order being reflected there. Really, the lanthanides and actinides, I'm going to change colors so that we can see what I'm talking about here. The lanthanides and actinides, which are these elements down here at the bottom of the periodic table, are the lanthanides and actinides, the intertransition elements down here. This is the F block, and really, this is not what the periodic table looks like. The periodic table really looks like this. Okay, where this was the S block, this was the F block, this is the D block, and this is the P block here. And so, because these elements are so rare, what we literally did was we took this section of the periodic table and cut it out of the periodic table, and then took the S block and shoved it up against the D block. And you can see that if you follow atomic numbers right here and right here, because right here is barium at element number 56. And if you start looking for element number 57, you're going to find it down here. Okay, so you really, 56, and then you have to come down here, and that's reflected in the order of filling as well. Right after the 6s comes the 4f. You can see that here. Right after the 6s comes the 4f. So really, these two rows are part of rows 6 and 7 in the periodic table. Row 4, row 5, row 6, row 7. So these two rows really fit in there. So if you were to cut apart the periodic table, you could literally take those two rows, the lanthanides and actinides, and put them back in the periodic table there to show the order of filling there. Okay? All right, but just wanted to show you that you can literally use an element's position in the periodic table to figure out what ending it should have on its electron configuration. Okay? And that's going to be super useful, especially for what we're talking about next. Now, before we move on to the next slide, I want to point out how the electron configurations for noble gases are going to end. the electron configuration for neon, which is right here, is the last element in the 2p. Remember, p holds up to 6, and you can see this is 6 boxes wide. This would be 2p1, 2p2, so on until you got all the way up to 2p6 here. So this would be 2p6 for neon, would be the ending of its electron configuration. I bet you can guess what the electron configuration would be for argon then. It's the same thing, just an energy level higher. It would be 3p6 here, 4p6 here, 5p6 here, and 6p6 here. And so knowing the ending on those noble gas core electron configurations can save you some time for what we're going to be taking a look at next. Speaking of, we've looked at orbital diagrams. That was boxes and arrows and the standard electron configurations, the 1s2, 2s2, 2p6 stuff. There is an even shorter way to write an electron configuration. Let's do an example. All right, so for example, let's take a look at an electron configuration for something like, scandium. All right, scandium has an electron configuration, if you were to do the standard one, that has 21 electrons in it. Okay, so quickly that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's up to 20. I've only got one left. We go to 3d, and I've got one electron left to put in the 3d. Okay? Now, if you identify the noble gas that comes before that atom, then what you're going to do is basically use the period number that noble gas atom is on, which is going to match the highest energy level of that noble gas, to help you know how much to substitute for it. Another way to think about this is we're using a noble gas to stand in for part of a larger electron configuration. So if you were to say back up in atomic number from scandium until you got to the previous noble gas, back up from number 21 to 20 to 19, you'd hit argon, which would be something with 18 electrons. Well, how much of this electron configuration would be the same as argon's electron configuration? If you start looking at adding up the little numbers, you'd have to add up all of the electrons up to 3p6 to get your 18 electrons, which would be the same as argon. And so the effect here is that if you want to write scandium's electron configuration in a shorter way, then the noble gas core electron configuration for the exact same element would simply be written as argon in brackets, and then you just have to include what was not already inside argon's electron configuration. So whatever's at the end, you'd have to include the 4s2 and the 3d1 there at the end. So this is a way to write scandium's electron configuration. Notice it's a whole lot shorter than this big old thing. Okay? All right, now, if you combine this technique with the previous technique here, of knowing what the ending on the noble gas core electron, or what the noble gas's electron configuration would be. You know, they're all in the p block, and they all in a p6 that matches their row, that matches their period. Then, I could say, okay, if argon's in the third period, the last where I'm going to leave off is automatically going to be a 3p, because that's where argon finishes. So then you could just look at your arrow diagram or look at your periodic table to know where to pick up from there. And so you wouldn't have to do this first. You could go straight to this if you know where argon would have left off. And that's the idea I'm trying to get across here, where it says write the period number that the atom is on. I should say write the period number that the I would say figure out what the period number of the noble gas is, because that's where the noble gas is going to leave off there. Okay. All right, so that's known as a noble gas electron configuration. It's also called a valence shell electron configuration, another term for the same thing there. Okay. All right, that's all we have time for in this lesson, and we'll see you next time.